To explain the singular value composition, we're going to continue using the twin height example. It's shown here on the left. The data is shown. We're plotting the two heights in a scatter plot. And then on the right, we're showing the rotation that we already found to have the property that it can be used to reduce the dimension if, for example, we want to preserve distance considering only one dimension. So in this case, Z1 is the dimension that does that. The transformation we're applying is shown and down here. So we're going to see how this relates to the singular value composition. Turns out that you can get this transformation using singular value composition. So let's look at what it is, what the singular value composition is in general. We can write any matrix, M and matrix Y, with three other matrices, U, V, and D. U and V are orthogonal, and D is diagonal. And they have the property that U transpose Y equals D V transpose. And we're going to see why that's powerful when we apply this to data. And a very important characteristic is that the sum of squares of VD or UD are decreasing. That's going to be a key useful fact that we use, for example, for dimension reduction. And I'll note that the more common way to represent this transformation is shown down here. It's equivalent to this form that I find slightly more interpretable. So here's an important characteristic. If you take the cross product of UD in itself, so UD transpose UD, that's going to give us the sum of squares of the columns of UD. And if you do the math here, because U is orthogonal, cancels out, and you are left with D squared. So this tells us that the entries of D, if you square them, it actually tells you the sum of squares of UD. That is going to come in very, very soon. So note that if we, just so you can start seeing how this is useful, if the last k entries of D are 0, that means that we can take out k columns from U and V, then recover the Y after that, after removing those dimensions, so we're reducing dimensions, and we recover the data. So we're going to see that using our code. We're going to apply this to actual data. So let's try that out. First, let's start by creating this twin height data set. It was a simulation. We can take a quick look by plotting y1 and y2. I'm going to keep the x limb and y limb fixed. So let me define what I want that to be. Let's do minus 3.5 to 3.5, so we include all the points for sure. All right, and there you have it. You can see the points, the twin heights that we've seen before. And now what I'm going to do is I'm going to apply the singular value composition and show you that it actually gives us that rotation that we saw that has those properties. The transformation has is based on an orthogonal matrix, and it has the variability of the columns decreasing, so we have the first dimension having much more variability than the first. So let's just do that real quick. SVD of y. Okay, and if I now I'm going to call this PC1 because we'll later see that this is actually the first principal component. I'm going to look at D times V. Right, so the U, V, and D matrices are included in the in this object S. So I'm going to take the first column, and then I'm going to take the second column, multiply it by D. These are the columns of D times V, and now we plot this. We plot these as well. Let's now plot PC1 and PC2, and we see that we obtain the rotation that we have seen before. Whoop, PC2, sorry. Let's do this one, and there it is. See the rotation that we did previously? So the singular value composition gives us that rotation that was giving us the first dimension with a lot of variability explained, so that it preserved the distance. So we're trying to get a hint of how this all is connected. So later we'll learn that the singular value composition is related to principal component that explicitly tries to find rotations that maximize the variability explained by the first column of the U or V matrix. Okay, so now let's apply this to some. Let's look at some real data that's a little bit more complicated than the simulation that we've looked at. I'm going to load this library called tissues gene expression, and then I'm going to load the data set with that same name. That's this is a pretty big data set. We can look at the dimensions of it. It's 189 samples. It has several tissues. We've seen this one in a previous video. So the first thing I'm going to do real quick, just to simplify things, is I'm going to remove the units. I'm going to standardize the data set. So I'll standardize the columns. I'm sorry, the rows of V. It would be done like this with the function scale. I'm going to do something else just so that the video goes a little faster. I'm going to only use, let me set the seed so it can be replicated. I'm going to only use the 500 rows. You can do it with all the rows. It should work out the same, but this will go a little faster. So how many should we take? 500 maybe. 500. Okay. Okay. So there we have it. Oh, making sure this is all good. We need to get rid of this, and it's end. All right, that should do it. Yeah. One more parentheses. Okay. So now we have this scaled matrix, and now I'm going to apply the singular value composition. There we go. And what I want to do first is I'm going to, just so you can follow along with the math that we showed, I'm going to define these letters so it matches the notation. And then D is, so this returns a vector. SD is just a vector, so I'm actually going to turn it into a matrix, just so it's exactly like the math. All right, so first thing I want to show you is that you can reconstruct Y by using that formula. So let's just confirm that the SVD actually did what we think it did. Let's put some spaces here so we can see it better. So what's TV? Right, so that define these guys, and this should give us the this should recover Y. So let's define these residuals. And see if these should be the same. Okay, so let's try that. So let's see what is the biggest residual here. It should be a very small number, pretty much 0. There it is, very, very small. Okay, now next step. Let's quickly look at the entries of D to see if we have anything that's very, very close to 0, so we can start reducing dimensions, getting rid of some of these dimensions. We have 200 samples here. Maybe we can make it a little bit. Is it 200? Maybe, I can't remember. 189. So let's look at that. So let's plot S of D. What's going on? Come on. It's not letting me do anything. S of D, very quickly, and you can see already towards the end there seems to be some D's that are actually exactly 0. So let's get rid of those. So what I'm going to do is I'm going to define K. Actually, here I'm going to switch it from what I showed you in the slides. This is the number I keep, not the number I get rid of, just to make it a little simpler. Now I'm going to reconstruct Y, but now I'm only going to use the I'm going to remove those last 4 columns. Right, so this is how it would work. Right, so I'm reducing the dimension of the problem by 4. Not terribly exciting, but it's a start. Okay, so now I do this, and let's see what the residuals look like now. Let's copy this guy over, and what is the max now? It's going to be pretty close to 0. Look at that. Yeah, so removing the last 4 columns, we keep it exactly the same. So we already achieved a little bit of a reduction. All right, so now let's see what happens if we can do more than that. So one of the useful results coming out of the singular value decomposition is that the entries of D actually tell us the proportion of variance that is explained by that particular column. So if I plot SD squared divided by the sum of all the SD squares, and I'll multiply by 100, so it's percentages. That shows us the percent explained by that column. So we see that the first dimension of this transformation, U, this rotation, is explaining 20% of the variability, and it drops down quite fast. You can see by the time we get to 100 or so, we are pretty much at 0. So now we're going to try something a little bit more drastic. Let's remove half of the data, half of the dimensions. Right, so now it's 95. So how much do we recover now? So what we're going to see if we, for example, plot box plots of the residuals. Now it's not going to be 0 because we actually have removed a little bit. If we make a box plot of these residuals, and I'm going to make the y lim, what was it, lim, just to compare to the original data. And what we see is that we have very small residuals. So we are pretty close to the original y, even when we reduce the dimensions by a half. Right? And this transformation lets us do that. So we can actually answer what percent we actually keep by computing that. So we could take the variance of the residuals and divide it by the variance of the original y. Actually, I think we have to turn this into vectors because they're matrices. So let's do that. And we see that we recover a lot. It's more than 90%, right? So that's 4% is what we lose. So this is how much we explain, almost 96% by reducing the dimensions by a half. And we didn't have to do this complicated computation because we already had that answer just by looking at the D's. You can take 1 through k, right? We didn't even have to compute residuals because this D's answer exactly that question. A 1 over k, all of them. Oh, we have to square it. Okay, and that should give us the same answer, 95.8%. Yeah. So 1 minus. Whoop. Oh, sorry, no minus that like that. Okay, there it is. See, actually, it's the exact same number. All right. So we could give other examples of how this is useful. One thing we could do is create a highly correlated matrix and see that the dimension reduction is even more greater. In a later video, we're going to talk about multidimensional scaling, which uses these results to make exploratory plots, exploratory data analysis plots of high dimensional data, taking advantage of these properties of the singular value decomposition. But just to give a final example, we'll very quickly create a simulation where we have highly correlated data. I'm going to create a vector norm just with 100 data points, and then I'm going to create a error structure. Yeah, let's do a bigger one, 25 columns. Let's just add some noise here, but a very small amount of noise, so it's practically the same data with a little bit of change. That's what y is going to be. Actually, let's just do 2. Okay. So it's now I'm going to do 2. And what we see is that if it's something like this, you can very quickly see this data is very correlated. You can see that the singular value decomposition, if we compute it for this thing, for this particular data set, you get that a lot of the variability, most or almost all of the variability is in the first column. So let's just do this. Yeah, so pretty much all of it. When you have highly correlated data like that, you can reduce the dimensions greatly, and you can create an example with more columns that are highly correlated and get a similar answer. Okay, so that should start giving you an idea of how the singular value composition is useful. We're going to keep using it, and in data analysis, and you're going to start getting even more of a feeling for that.